Now, today we will do the decision tree, and the decision tree and random forest. The last two things are remaining in supervised machine learning. Now, decision tree is a huge thing, and random forest. If we don't understand decision tree, we will not able to understand random forest. So we will discuss today about the decision tree, and in the next class, which will be the last class, in that class we will conclude the decision tree and the random forest, and that may be on the next week of that may be in the next week or starting from Monday to Friday, any day. So we will uh, conclude this supervised machine learning uh, algorithm. So we will discuss today about the decision tree, and to some extent where I will show the the coding, few part of coding on the decision tree on the not today and the next day. The not few part I will show the how the decision tree can be made, and it can be visualized, it can be trained using some code. See, when you are coding something, you have to understand what I have to write and what I have to create. In that respect, I have to code. And if you don't know the theoretical basis, you cannot able to code that particular thing. So you have to know theoretical something about that particular algorithm. I don't say that you have to know in depth, but because in industry we will main focus is on coding. So in that respect, if I want to code something, then we have to uh, we have to realize and we have to learn about what is the theoretical basis behind this. Otherwise, we cannot able to code if any project comes. So we have background. We must have a background. It may be a not in-depth knowledge, but we must have a background on the theoretical basis. What coding, how we proceed for the coding. I will just explain that uh, that part of the decision tree, that is which part is necessary for the coding, the theoretical which part is necessary for the coding. I think that this prospection is totally explained in the previous class. So decision tree is based on what is the main concept. The decision tree is based on basically you have to create a root node, and with that respect, we have to create another child node. So Shelly starts the following of the parent node of 49,929 observations. So this is basically a data set. Our data set is given of 49,929 observation, and we have to segregate that data set in the term of the uh, classification analysis using the parent node and the child node, and where the converting percentage is 38% and non-converted is 63%. That means the actual value is the 38% and non-converted portion is 63%. So splitting the decision tree, the name of the tree is the decision tree, and the feature selection. Now, how I divide the predictor variable that has been explained over here, that Shelly can split the parent node into two or more child nodes using any of the predictor variables. So the predictor variables are already given in the data set, and we can split the parent node with the respect of the two or more child node. That can be done, and Shelley explores using such predictor variable as splitting variables. Explores in, using each predictor variable as splitting. The Shelley groups the continuous variable or the categorical variable two or more buckets. So this two or more buckets means two or more groups, similar to where similar to what is during the variable meaning. It calculates the chi-squared statistics with respect to the with respect to each of the group predictor against the target variable that converted. So we are data set is given having the predictor and target variable. We are dividing the predictor variable, and we are exploring the predictor variable and splitting the variables. How the splitting is taking place? The splitting is taking place in the form of groups. So grouping is based on the continuous variable or categorical variable. Right. Now, Shelly also, now this grouping of the parent node with respect to child node, and then again another child node is created with that respect to that particular child node, the other child nodes are created. And that the other child node, when it is created, then the previous node is a parent. We all know these things. So now how this grouping is taken place? Now this grouping is taken place with respect to this, how this grouping is taking place against the target variable is taken place by means of the chi-square statistics. That is the chi-square distribution. Right. So with the chi-square distribution, so price state chi-square distribution. So grouping of the parent node with child node, again the child node with parent node, again child node. This total thing is taking place with respect to the chi-square distribution. So what is chi-square distribution? Chi-square distribution is f of x square is equal to e to the power x square by log c minus 1 to the power x by x2 by. So it is basically a continuous distribution. It's a continuous distribution. It has the zero value at the lower limit and extends up to the infinity in the positive direction. It has only one parameter, that is this v. This v is basically nothing but the degree of freedom. Degree of freedom. The Z stands for the variance. Chi-square distribution, the chi-square test is given by another formula, which is basically x of square is equal to summation of 2 minus e minus e square by. So this is the formula of chi-square test. Right. So where O is basically, this O stands for the observed frequency. Observed frequency. And E is the expected frequency. So this is basically a predictor and this is basically a target. So when I'm talking about respect to decision tree, will be the chi-square test. What will be the chi-square test? So chi-square test is x square, which I showed you just now. X square is equal to summation of y minus ei, y by ei whole square by the expected value, that is v of y. So O is basically the observed frequency, E is the expected frequency. So E is basically the predictor variable and so grouping is done from the data set. The grouping is done with the help of the chi-square test. Understood? This is a chi-square test which I showed you. This chi-square test is equal to summation of y minus ei whole square by ei. O is the actual value, is the predicted value. Is termed as the observed value and is the expected value. So for instance, with gender as potential, the splitting variable Sherry obtains the following tabulation, which yields the chi-square test. So there are convert and non-converted. So for gender mode, these are the two parameters which we want to check, that is the convert and non-convert. And these are the tables where the various attributes are given. Gender female and the girl. So there are some figures that converted and non-converted. Now the split of the parent node into child solely selects the predictor variable that yields the maximal value of the chi-square test. So how should I divide the decision? So in order to create the decision tree, that is the creation of the parent node with respect to the other two child nodes. So from the table, we have to check the chi-square test or chi-square statistics from which we want to get to the maximum value of the chi-square test. Right. So we can apply. If the maximum value lies, then only we can apply and find the chi-square value for the highest job time. So here we are creating all the attributes are given over here. You see that the job time has the highest chi-square test. So the variable which gives the maximum value of the chi-square statistics is the job time. So that variable will be divided into two subgroups. To split the first child, pardon, Shelly again selects the predictor variable that yields the maximum value of chi-square. So how the splitting can be done? That is the splitting of the parent node with two child nodes and again with one child node. Again, I'm creating two child nodes. So this, how this it becomes a decision tree-like structure, and this so this splitting method of the child node, parent node into the child node, as I told earlier, that it is done by the chi-square statistics. So we split the gender with chi-square step. The marital status is 0.006, job type, the gender is 0.06, marital status 0.02, job type is 14.3210. The age is 8.262, income is 2.2321, current coverage is 5.638, family size are given, and the current product type is also given. So all these figures are the chi-square test. So here also the variable that yields the maximum value of chi-square statistics. So I am dividing. So here gender and chi-square, the marital status, the job type gets the maximum value. So with respect to this job type, I am dividing it into the two nodes. So high, this is out of 40,929 observations. The convert is 38, non-convert is 62, splitting over there with 38 and 62. So there also I am saying the high conversion ratio because converting percentage is 74 and non-converting is 26%. However, the convert is 8% and non-convert is 12. So less conversion ratio is not as the less conversion ratio. But this node 1 has one type of conversion ratio, and this node 2 has another conversion ratio. So there is a disparity of the two nodes. So splitting the decision tree further, when I want to split the decision tree further, Shelly again selects the predictor variable that gives the maximum value. So if I want to split the decision tree further, the Shelly again selects from the predictor variable which leads to the maximum value of the statistics, chi-square statistics. So here we again saw that the current coverage has the highest chi-square value. So we split the road into the current coverage. Splitting the child node, Shelley does not consider the job type as the potential splitting variable within the node. Splitting the chi-square, splitting the change decision tree part. To split the first child node further, Shelley again selects the predictor variable that gives the maximum value. So every time the maximum value, which has the maximum value, I considered it as a node. From here, I am calculating the two child nodes. So it is seen that this node has high conversion ratio, and this node has low conversion ratio. So So here also again we are splitting the node with two blank channels. Now when we drop this splitting of the decision, we must do not continue this process, that is splitting the node, the parent node into two child nodes in a prolonged manner. So what will be our solution to stop this splitting of the decision? We have mentioned that the minimum size of them. So Shelley could predefine the minimum size of them, that is proportion to the observational node. Then if node contains like then the predefined observation she should stop the splitting the node. As thumbed in the in several, the minimum size of the node is a set of that the minimum size of the node is the set of 2 to 5% of the observation. So the minimum size of the node is the Shelley could predefine the minimum size of, that is the minimum portion of minimum proportion of the observation. Here also we use some thumb rule. A thumb rule in several minimum sizes of node is a set that has less than 2 to 5% of the observation in time. So the next point is a thumb rule in several the minimum size of the node is less than, should be less than 2 to 5%. Of the entire data set. Now, the depth of the chain dissection tree. So the chaining we could redefine the maximum number of layers of this splitting. A complete homogeneous node. If the Shelly arrives at the node that is completely homogeneous with respect to the Shelly, the a complete homogeneous node if the Shelly arrives at the node that is completely homogeneous with respect to the target variable, then she should stop the splitting the node further. For instance, if the Shelly finds that all the observations in particular node are given, then we say that it will be converted or not converted, then we should not split in the node part. I have another question that created this thing. So no incremental benefit of splitting the node further. If the Shelly finds splitting the node further does not provide an incremental benefit, then she should not split the node further. Now, so in this article, so how we created this attribute selection measures means how we created the predictor variable. So attribute selection measures a heuristic and for selecting and splitting criteria, that is partition of data in best possible manner. It is also known as splitting rule because it helps us to determine the breakpoints for tuples on a given node. ASM or attribute selection measures provide a rank to each feature by explaining the given data set. So we have a data set will be given and we have to explore that particular data set, and in that case the continuous value attribute I will use basically the continuous variable rather than the digital rather than the non-continuous attribute. In case of contiguous value to attributes, the point, so the split points for branches and also need to define the most popular selection for information gain ratio and index. So the information gain with respect to the splitting of the nodes is given by these three formulas. Now, we have to know the entropy. So, what is entropy? Entropy means entropy is basically used in a communication where there is a theoretical paper which is basically taught in the electronics and electrical. So entropy is an information theory matrix that measures the impurity and the uncertainty in a group of observations. So entropy is an information theory metric. It is basically a metric that measures the impurity of uncertainty in a group of observations. So this is entropy, and these are basically the formulas. Info D. So here it is said that information gain is the decrease of entropy. Information gain computes the difference between entropy before split and average the entropy after split of the database and data set based on the given attribute value. So these are the formulas. Info of D is equal to summation of mi to m pi log to plus pi. Another is the information D is equal to summation of E v2 j dj by mod of dj mod of d. That means there should be information d. This entropy must take the positive value because the absolute sign is given. So if any negative sign comes over here, we have to give a positive sign using the appropriate value. So here it is, all the parameters are given over here. Information D is the average amount of information needed to identify the class level of the tuple D. Now dj oblique D acts as the weight of the J first. So these are basically the dj of big D acts as the weight of the jth partition and D is the number of the discrete values in the attribute A. Now, J is basically the partition number and B is the J is basically a partition number and B is the actual value. So right. So here P stands for the probability. So information B is equal to minus summation of I to n pi log base 2 probability pi. Another information is given, the summation of the G equal to 1 to B mod of dj by d into d, right? So here also this I am the two things. One is the B, another is the J. J is the partition number or the weight of the partition. Starting value is 1 up to the last value of the B. Now, similarly, the M over here is starts with I equal to 1 to the last value of M for calculating the probability. Now, here the which is explicitly written that information P is the average amount of the information needed to identify the class level into the tuple B. So dj and D acts as the weight of the jth partition. So these are basically the weight of the jth partition. Information A or sub P is the expected information required to classify the tuple from the D based on the partitioning by E. So this is the coding we will do on the next week. If it is possible, then I can show you on Saturday or Sunday. This is the coding part. We will start it from tomorrow. Have you understood this thing?
Yes.
So in the next class, we will proceed after from the gain ratio and we will do this coding part. Whole coding part we will see. Right?
Yes.
The last class, the next class will be the last class. We will do the coding part of the decision tree and we will do the random forest, both the theoretical part and coding part. So the next class will be the last class of this data science. It may be on Monday or Tuesday, but that should be the last class. Right? So any problem from this theoretical point of view, this theory will not come in your industrial point of view, but you have to, once you want to code, you have to know the theory. So that is the, just a touch the theoretical touch is given. So, any problem, any question? Okay, so on the next day, we will, that may be Monday or Tuesday, we will do the coding part of decision tree and random forest. Rajkumar, any problem? No.